Welcome everyone. What we're going to do today is we're going to talk about intermolecular forces. And what you're looking at here is the states of matter. You're going to notice that one of the fundamental differences between states of matter has to do with the intermolecular forces of attraction between them. If you look at solids, notice they're very close to each other. They're very organized. And because the particles are close to each other, they have very strong intermolecular forces. When you look at the liquid phase, the intermolecular forces are not as strong. There is some freedom for the particles to move around when you're on that liquid phase. But notice that in solids and liquids, pretty much the intermolecular forces are they're a little stronger, especially compared to gases, because the particles are relatively close to each other, especially in the solid phase. These two states of matter are also referred to as condensed phases due to the proximity of the particles to each other. In the gas phase, intermolecular forces are very weak because the particles are very far from each other, and that also allows the freedom that you see with gas particles. Now, if you look at this molecule here, you'll notice that between the hydrogen and the chlorine, there is an intramolecular force. The example here is a covalent bond. An intramolecular force is within the molecule. It's holding the H and the Cl together. Now, notice there are two HCl molecules. An intermolecular force is between two different molecules. The word inter means between. And what you're going to see is that the attraction between these molecules, they're not as strong as intramolecular attractions. In other words, intermolecular forces are way weaker than intramolecular forces. I'm going to give you the examples of each in just a moment. What is neat is that many physical properties have to do with the intermolecular forces. We're going to see how intermolecular forces plays a role in determining boiling point, melting point, viscosity, surface tension, as well as capillary action. Now, these are the examples of 4 intermolecular forces. Now, they're all weak compared to intramolecular, but you'll notice even these don't have the same strength. The weakest of the intermolecular forces are known as dispersion forces, also known as London dispersion forces. We usually refer to them as LDFs. And one of the things you're going to learn about these guys is that they are the weakest of the intermolecular forces, and all compounds have LDFs. Every single compound and atoms possess London dispersion forces, okay? And you'll see that this is the predominant force between nonpolar molecules. The second one is known as a dipole-dipole force. It's a little stronger, and this is the one you will find between polar molecules. And then we have a special dipole-dipole force that is stronger than your ordinary one, known as a hydrogen bond. So that's the third type of intermolecular force. And then the strongest of the 4 is known as an ion dipole force between a polar molecule and an ion. Now, these 4 are ranked from weakest to strongest as we go down this way. But all 4 of these are much weaker than an intramolecular force, which I will show you in a moment. Now, the first 2, the London dispersion forces and the dipole-dipole forces, are also collectively referred to as van der Waals forces. Okay? Now, let's take a look here. So, we know we got intramolecular versus intermolecular. And one of the key things is these are the stronger ones. And then we got ionic, okay, which is probably the strongest if you compare melting points. Ionic bonds are stronger than covalent bonds. They have higher melting points. So we're going to put here covalent bonds. Those are 2 of the main types. And there is a third that we call a metallic bond. These are all intramolecular forces. These are within the molecule. And then in the previous slide, you saw the intermolecular, which is the LDFs or dispersion forces, the dipole-dipole, the hydrogen bonding, and the ion dipole. So you got the intermolecular forces and the intramolecular forces here, okay? And again, if I had two water molecules, let me draw two molecules here. The line, the solid line that you see would be a covalent bond. That's an intramolecular force. And then I'm going to draw another water over here. When you have a force between two molecules, which I'm drawing here with a dotted line, that one you'll learn is a hydrogen bond, and that's an intermolecular force, and that's much weaker than an intramolecular force. So we're going to talk about dispersion forces, okay? Now, the figure it says below on the next page, actually, we're going to show you how dispersion forces are the force of attraction between nonpolar molecules. We're going to use helium as an example, and we're going to talk about something called polarizability, okay? Polarizability is a term I want you to know. It's the tendency of the electron cloud to distort itself. And some things are very polarizable, some are not. And it has to do with the electron cloud. As electrons randomly move around, they can become polarized. Now, what you will learn is that this happens for a split second. When they become polarized, they don't stay that way. It's basically what we call a temporary dipole. We'll talk about that in a moment. I'm going to show you an example using helium. So on the left, you have two helium atoms labeled atom A, atom B. And notice that the two electrons that helium possesses, they're just randomly moving around. But look what happens when you get to the middle diagram. Notice in atom B that for a split second, as the electrons are randomly moving, they go to one side of the electron cloud and not the other. For a split second, atom B has become polarized. Notice on the bottom over here how for that split second when the electrons are on the left side, represented by the blue shade, notice how it has become what is called a temporary dipole. It becomes partially negative on one side and the other side is partially positive. Now we call this an instantaneous dipole because it happens for a split second and it actually reverts back to normal. So this thing is going back and forth. It becomes polarized for a split second, then it goes back to normal. Now, here's what's interesting. When the atom B becomes polarized, which we call it an instantaneous dipole, it has an effect on its neighbor, which is atom A. Notice what the effect is going to be. If you look at the third diagram over on this side, notice that atom B is already polarized, but look what it's going to do. The electrons are going to cause the electrons from atom A to shift to the other side, which you can see here in the third picture. So what's happening is atom B is influencing atom A to become polarized, and for a second, both of them become polarized. Now, the original one was the instantaneous dipole. As a result, the neighbor got polarized. We call the one that gets polarized as a result an induced dipole. So for a split second, I'm going to draw this on the bottom. We have atom A becomes polarized. I'm going to draw it like this so it's more visual. Okay? And they're temporary dipoles. All right? This is just for a split second. There's a little attraction when they become partially polarized, and that attraction just lasts for a split second. Well, guess what? That little attraction that lasts for a split second is what we call a London dispersion force. It's what causes nonpolar molecules to interact. It's very weak because it only lasts for a split second, and it is between two different atoms or two different molecules, as you can see here. Now, here's a better picture. Notice in frame 1, helium, the electrons are just moving randomly. And as they're moving randomly, as you can see in frame 2, All of a sudden, as the electrons are moving around, notice how they go to one side of the electron cloud. In frame 3, this becomes polarized. This side becomes more negative than the other side. So this just became an instantaneous dipole. Now, watch the effect it's going to have on the neighbors. If you look here, let's say the instantaneous dipole was the middle one. Here's the neighbor to the left. We'll take a look at this neighbor. Because of these electrons, it will cause the neighbor's electrons to get pushed to the other side. There also will be an attraction over here between the nucleus and the electrons. So, the neighbor becomes polarized as a result. This is what we call an induced dipole. Notice what it says at the top. An instantaneous dipole on any one helium atom will induce an instantaneous dipole on a neighboring atom. So the neighboring atoms, once they both become polarized, they will attract one another. Notice there's a partial positive and a partial negative. That's the attraction that is occurring between the neighbors. This attraction is what we call a dispersion force or a London dispersion force. And again, it's between two, in this case, two heliums, and it is a very weak force of attraction. Okay? Now, let's look at some of the factors that will affect the amount of dispersion force within a molecule. Okay? Here's the key. The number of electrons in an atom is very important. The more electrons there are, the greater the dispersion force. What you're going to see is that London dispersion forces have to do with polarizability, which is the distortion of the electron cloud. The more electrons there are, the greater the polarizability. The greater the polarizability, the stronger the London dispersion force. So the size of the atom or the molecule, which has to do with the molecular weight, plays a role because larger atoms, larger molecules will have greater electron clouds, which will lead to greater polarizability, and that will increase the strength of the LDF. Also, we'll see this a little later, but the shape of the molecule also plays a role. If you compare two molecules with similar masses, you will notice that a linear molecule, which you see on the top there, has more surface area contact with the neighbor. And we'll go back to this and we'll see this later. But when you're linear, there's more contact. So the more contact there is, the stronger the London dispersion force. When you're more compact, like in the bottom structure here, this spherical molecule is more compact. Notice there's less contact between the molecules. There's less surface-to-surface contact. Now, we're going to see that the stronger the London dispersion force, it's going to have an effect on certain physical properties, and we're going to be looking at boiling point in just a moment. Okay? You can already see here that the boiling points are affected differently. Okay? Notice that the linear molecule has a much higher boiling point than the spherical molecule. Again, we're going to look at that in just a moment. Also, this is going back to the size of the instantaneous dipole. All right? The magnitude of the instantaneous dipole depends on several factors. We mentioned polarizability of the electrons. So the larger the volume of the electron cloud, the more polarizable something is, which will lead to a stronger attraction. You can see what I wrote here. It says larger molar mass means that those compounds have more electrons. The larger the electron cloud, the greater the polarizability, which at the end of the day means a stronger London dispersion force, a stronger attraction between the molecules. And we saw how shape plays a role. We saw that when the molecule is linear, there's more surface-to-surface contact, so the LDF is stronger. When you have a more compact structure, you'll see that there's less contact between the molecules, and less surface-to-surface contact will result in a weaker interaction. So a weaker London dispersion force will result, will be the result. So look at this last slide here as far as the effects. Notice we already talked about the effect of molecular size on the strength of a dispersion force. So as the molar mass increases, okay, the number of electrons will also increase, which is the key. It has to do with the number of electrons being greater. So the more electrons, the greater the polarizability, therefore the strength of the dispersion force will definitely increase. And one of the things we're going to look at is, notice the stronger the attractive force, which has to do with LDFs, the higher the boiling point will be. And that's something we're going to look at in a moment. So the greater the London dispersion force, you'll see the effect it has on boiling point. Substances will have a greater boiling point. You see, in order to boil something, what you have to do is you're going from a liquid to a gas. When you boil something, you are not breaking any intramolecular forces. What you need to do is separate the molecules. What that means is that you got to just break the intermolecular forces. So if the intermolecular forces are stronger, it takes more energy to break them, so the boiling point would be higher. Okay? So you're going to see that substances that have greater LDFs will require more energy to cause the molecules to separate, which means that they will have higher boiling points. Here's an example. If you look at the red, you're comparing the noble gases, okay? And now we're going down a family here. So we got neon and then argon. So you're going straight down a family. Now what's happening here is the neon has less electrons. So the neon polarizes real easy. It doesn't really have a lot of electrons. And since it has very few electrons, it's not as polarizable in terms of the distortion of the electron. It won't get as distorted. It just polarizes really easy. And what's going to result is a very low boiling point. You'll notice it's in Kelvin. 27 Kelvin is the boiling point of neon. Now notice as you go down, the argon's boiling point increases, krypton increases. By the time you get to xenon, it's at 166 Kelvin. What's happening here is that as the atoms get bigger, there is more and more electrons, so their electron clouds are huge. So what ends up happening is the electron cloud, once they get distorted, it's way more polarizable, which will result in a stronger LDF, causing their boiling points to be higher. And you can see the blue lines are the halogens. And the same thing's going on when you look at the halogens. You know, you got fluorine at the top. These are diatomic. That's why they put the two in their natural state. But you'll notice that, you know, fluorine and chlorine are actually gases at room temperature because their intermolecular forces are very weak. So you'll notice 85 Kelvin is fluorine, okay? And then you got 239 Kelvin for chlorine. Now, when you get to bromine, you'll notice that bromine is actually, the boiling point is 332. It's actually a liquid at room temperature. And iodine has the highest boiling point at 458. It's actually a solid at room temperature. And a lot of that has to do with the fact that as you go down the family, there are way more electrons, which means it's more polarizable. The greater that electron cloud gets distorted, the stronger the force of attraction between these molecules, so the LDFs will be higher. And as a result, greater LDF means a greater boiling point. Okay, here we're comparing some hydrocarbons. You'll notice on the x-axis, you got the molar masses. So notice a pentane has 5 carbons. Its boiling point is somewhere about, 37, 38 degrees Celsius. Then you see hexane, heptane. Notice the number of carbons and hydrogens is increasing. And notice as the molar masses are going up, what's happening is these atoms have more electrons. And that's the key. There is a connection between molar mass, but molar mass is not directly what determines the LDF? It has to do with the increasing number of electrons, and it is true, as the molar mass increases, you will have more and more electrons, and that's really the underlying reason as to why the LDFs increase. So notice nonane molar mass is above 125, and if you look, it's probably somewhere around 150, 152, somewhere in there, in that vicinity. But you can clearly see that as you compare these hydrocarbons, as they're getting bigger and their molar masses are increasing, they have more and more electrons, which makes them more polarizable. And at the end of the day, their LDFs will be stronger, and that's why they have higher boiling points. So let's go back to something we mentioned earlier, comparing branched versus straight chain hydrocarbons or isomers. The straight chain isomers have, if you think about it, you have two straight chains. There's more contact between them, more surface to surface contact. Remember that we're trying to separate the two from each other. Okay? That's our objective when you're boiling something. You're trying to separate them, and it takes more energy to separate compounds that have straight chains because there's more surface to surface area contact between the two molecules. When you have a branch chain, so let's do a little branch here and a little branch here, notice that the only contact, notice how much less surface to surface contact there is. And because there is less surface area contact, it's easier to separate. We can separate these two a lot faster. Therefore, the boiling point of a branched chain will be lower than its straight chain counterpart. And I'm going to show you an example in just a moment here. You'll see we have two molecules here that have the exact same molar mass. Pentane and neopentane are isomers of each other. Pentane is the straight chain form. It has 5 carbons. And neopentane also has 5 carbons, but it's branched. So if you look, if you want to separate here the two pentanes, look at all this contact here. You have to separate all that contact in order for it to boil, and that's going to take more energy. So that's why pentane will have the higher boiling point, whereas neopentane, look at the little contact between the molecules. So this one's going to be a lot easier to separate. So this one will have the lower boiling point, as you can see here. So here's the same two molecules. I had shown you this earlier. When it's linear, there's a larger surface area contact. So pentane has a boiling point of 309.4 Kelvin. Now notice the neopentane, same exact molar mass. Notice it's compact, and as it's compact, there's smaller surface area contact. The LDFs here are going to be easier to break. So notice that the boiling point is only 282.7, way lower than the boiling point of the linear version, which is pentane. Okay? So this video was exclusively on London Dispersion Forces, or LDFs. They're sometimes just referred to as dispersion forces. And one of the things I want you to remember is that this is the main force of attraction between non-polar molecules. And you will also learn, as we continue to look at other intermolecular forces, that all molecules, all atoms, possess LDFs. Okay? In the next video, what we'll do is we'll go ahead and explain dipole-dipole, hydrogen bonds, and then the ion dipole. Those would be the other intermolecular forces that we were going to go over and then compare their strengths and how they affect other physical properties such as boiling point, melting point, viscosity, etc. Okay?